Welcome to this explainer. Today, we're looking at an absolute landmark piece of research, ImageNet classification with deep convolutional neural networks. Now, I promise you, this isn't just some dense, dusty academic paper. It is literally the blueprint that fundamentally shifted the entire landscape of machine learning, and we're going to unpack exactly how they did it.
Before we dive into the math and the code, I want you to keep this central question right in the back of your mind. For years, computer vision really struggled with realistic complex images. But this specific approach completely shattered that ceiling, proving once and for all that deep neural networks were the undisputed future. So how exactly did they do it?
We've got a lot of ground to cover, so here's our roadmap for today. 1. The object recognition challenge. 2. Inside the neural architecture. 3. The need for speed. 4. Defeating the overfitting monster. And finally 5. Those record-breaking results. Let's jump right in. All right, part 1, the object recognition challenge, grasping the scale.
1.2 million. Just let that sink in for a second. That is the massive number of high-resolution training images the researchers used from the ImageNet 2010 contest. And these weren't just simple geometric shapes. They were complex, real-world images manually spread across 1,000 highly specific categories.
Look at the stark contrast here. Back in the day, old data sets like Caltech or CIFAR had maybe tens of thousands of images, which, was fine for really simple recognition tasks. But ImageNet, we're talking over 15 million labeled, high-resolution images spread across 22,000 categories. Real objects in the real world have incredible variability, right? Different lighting, weird angles, cluttered backgrounds. Teaching an AI to handle that kind of chaos demanded an entirely new kind of engine.
Which brings us to part 2, inside the neural architecture, building the engine.
So what you are looking at right now is a blueprint of their deep convolutional neural network. It's a bit of a mouthful, I know, but the absolute beauty of a CNN is that it makes a very strong, mostly correct assumption. Pixels that are close to each other are related. By doing this, the network can process massive amounts of image data without its internal connections getting completely tangled up and mathematically impossible to compute.
And the really crucial point here is the sheer scale. Okay, sure, 60 million parameters might sound kind of tiny compared to today's massive language models, but back then, this thing was a behemoth. Packed with 650,000 neurons, 5 convolutional layers, and 3 fully connected layers, it was literally engineered from the ground up to soak up the vast amount of prior knowledge needed to actually understand the real world.
Moving on to part 3, the need for speed, overcoming physical limits. You see, traditionally, neural networks use standard equations like the tan function. These are what we call saturating nonlinearities. Essentially, that means their learning eventually plateaus and just slows to an absolute crawl during training. So, to fix this bottleneck, the researchers swapped in rectified linear units, or ReLUs for short. It's a non-saturating function that basically bypasses that whole mathematical traffic jam. And if you check out this graph, you can see exactly why that matters so much. That solid line? That represents a network using ReLUs. The dashed line is the traditional method. Notice how the ReLU network reaches a 25% training error rate, 6 times faster. Without making this switch, experimenting with a 60 million parameter model would have taken an impossibly long time to train, like literally unfeasible. But speed wasn't their only physical limit. Memory was a huge, huge issue. Keep in mind, a single GTX 580 GPU back then only had 3 gigabytes of memory. I mean, your smartphone probably has way more than that today. Because of this limit, they quite literally had to split the network's brain across 2 separate graphics cards. And the true genius of it? The GPUs were programmed to only communicate at very specific layers. This precise parallelization didn't just solve their memory problem, it actually ended up reducing their error rates. Talk about a win-win.
All right, part 4, defeating the overfitting monster. Now, even with 1.2 million images, a 60 million parameter network is going to be heavily tempted to just memorize the data instead of actually learning from it. That's the classic overfitting monster. To fight this, they basically gave the AI an endless supply of free practice material using data augmentation. First, they extracted random patches and horizontal reflections from the original images. Then, they dynamically altered the RGB color intensities using principal component analysis. It was basically teaching the AI, hey, a dog is still a dog, even if the lighting completely changes. And amazingly, they had the CPU generate these transformations on the fly while the GPU was busy training on the previous batch. Free data, 0 extra time.
Their second defense mechanism was this brilliantly simple technique called Dropout.
As this quote highlights, during training, they would randomly set the output of each hidden neuron to 0 with a 50% probability. Think about that. They were constantly shutting off half of the network's brain, essentially forcing it to work blindfolded. Because a neuron can never rely on its specific neighbors being active, it absolutely cannot get lazy. It's forced to learn highly robust, independent features on its own.
Finally, Part 5. Record-breaking results. The undeniable victory.
So, when you bring all of these elements together, the massive data, the architecture, the speed optimizations, the dropout, what actually happens? Well, the results completely redefine the field. Just look at these numbers. The previous state-of-the-art model hovered around a 45.7% top 1 error rate. This new network absolutely crushed that, bringing it down to 37.5%. And its top 5 error rate dropped to an astonishing 17%. For the scientific community, this was it. This was the definitive, undeniable proof that deep learning was the future of computer vision.
What is really fascinating here, though, is looking visually at what the network actually learned. Notice how it isn't just taking wild guesses based on whatever happens to be in the dead center of the image. Look over at the top left. It successfully identifies a tiny, way off-center mite. Or look at the leopard. Even when it's wrong, its backup guesses are highly plausible cats, like jaguars or cheetahs. The AI had developed a genuine semantic understanding of these visual categories. It wasn't just matching pixels anymore.
And if you want to know what the AI's eyes actually look like under the hood, well, check this out. These are the 96 visual features the GPUs independently learned in that very first layer. Because they restricted communication between the two GPUs, the hardware naturally specialized. GPU 1, up on the top, focuses heavily on shapes, edges, and frequencies, basically ignoring color. GPU 2, on the bottom, focuses almost entirely on vivid color blobs. It essentially evolved its own highly specialized split visual cortex.
The absolute main takeaway for you here is that in deep learning, depth is everything. The researchers found that if they removed even a single middle convolutional layer, which, by the way, contains less than 1% of the model's total parameters, the top 1 performance of the network dropped by 2%. It just goes to show you cannot cut corners. That sheer, unbroken 8-layer depth was the absolute secret to their success.
As we wrap up this explainer, I want to leave you with the exact same provocative question the researchers themselves pondered back then. If this deep convolutional network is capable of extracting such incredibly rich information from static 2D images, what secrets could it unlock when applied to the moving, temporal structure of video sequences? This architecture wasn't an endpoint, guys. It was the explosive opening of a massive new door. Thanks so much for joining me on this explainer, and keep questioning what the future of learning looks like.